This is the 2019 scholarship exam, question 2. Question 2. The circuit below is constructed with the following values for the respective components. We've got 3 resistors, an inductor, and an EMF cell is 100 volts. This is 100. And when you see these circuits, write the values above them. It just helps. 20, and that's 30 ohms. Currents respective branches are also indicated in the diagram. So we've got I1, I2, and I3. So current 1, 2, and 3. Calculate the values of I1, I2 immediately after the switch is closed. So after the switch is closed, the switch here, there's a rapid change in current. You could almost say that, the change in current with respect to time is such that L creates a voltage which is perfectly opposed to this one here. So if this is 100 volts, the initial voltage across the inductor will be 100 volts in that direction. So it'll be a back EMF, obviously, because that's what inductors do. So basically this here ends up being a short circuit, and we only have current going through I1 and I2. So I'll just say I1, the current will just go down through here. Nothing will happen through here. So I1 equals I2 as inductor has opposing voltage. Opposing voltage of E. Of the EMF. I've just chucked the funny E's. It's epsilon, but whatever. In other words, the current, so we'll just figure out I1 because whatever. Current is equal to the voltage, the EMF, divided by the resistance total. And these two are just in series with each other. So we're just going to have 100 divided by 10 plus 20 is 30. And that is going to be equal to 3.33 amps. And then we've got I1 equals I2, which is equal to 3.33 amps. There we go. Calculate the values of I1 and I2 a long time after switch S is closed. So a long time after switch S is closed, L has no resistance. Because if it did have resistance, it would have a dotted line around it, and then they'd chuck a wee resistor symbol in. But it's an ideal inductor, so they're just pretending the resistance of the wire and the inductor is non-existent. Have I spelled that wrong? Resistance, I haven't spelled that wrong. Resistance, so total, we'll find out the total circuit resistance. So R total is equal to these two in parallel, so the 20 plus the 30, so 1 over 30 plus 1 over 20, this is just the 12 inverted, and that would give me this branch plus the 10. And this gives me the total resistance. So the total resistance will give me the total current, which will be I1, and then I'll just find out I2 and I3, probably using like a voltage over that. So I'll just quickly calculate that out. And that gives me 22 ohms. So that equals 22 ohms of resistance. So I1 is equal to total voltage divided by R total, which just gives me 100 divided by 22, and that equals 4.54. So 4.54 5 amps, which is equal to 4.55 amps, because I'm going to round it up. Now I2, how are we going to do this? What is the easiest way? We'll just go find out the voltage of this one here, and then we can work out what the voltage to that was, and then we can just divide to find the current. That'll probably be the easiest way. So the voltage of R1, so I'm going to call this V1, is equal to 10 times 4.55, and that's going to give me 45.5. So V2, this voltage here, because it's just Kirchhoff's law, some of the voltages in a closed loop add to the supply, should equal 54.5 volts. So I2, and this is, I'm just going to call this V2, and this is going to be V1, V3, just for brevity, is equal to V2 over R2, and that equals 54.5 over 20. And we can see that equals 2.725. 2.7, it's rounded up to 3 amps. Right, next question. Calculate the values of all three currents immediately after opening the switch. So I1 equals 0 as it's in an open circuit. C-I-R-C-U-I-T. I2 and I3. I2 is equal to I3 as, there should be 3. They are in series. And immediately after closing the switch, the voltage here will be 100 volts, and it'll be 100 volts. Is it back EMF? Nah, it switches direction, doesn't it? Collapses such the current, I think from memory, goes this way, but don't quote me on that. I haven't bothered to try and, no, I'm not going to try and sit here and figure it out. You can use magnetic fields and hand wavy rules, but it's going to take me longer, and I don't need to know that just yet. So we're going to have I2 is equal to EMF of L divided by R total, and that's just going to give me 100 divided by these two added together, so it's 50 ohms, and that should give me, hold on, wait, 30 plus 20, is that actually 30 plus 20? I've just had a good think about this actually. This isn't entirely true. Immediately after reopening the switch, I3 will just be the current that was going through the inductor. The electrons can't really just boom disappear. I3 will just be the current that's going through that inductor. So I'm just going to cross this out. I just did this. I just thought about this for a second. I was thinking there's a blatant mistake. I3 will equal what was it? I1 minus I2, and that equals, what do we got? 4.55 minus 2.73. We have 1.82 amps, and this, we'll write down here, I2 equals I3 equals 1.82 amps. There we go. And the reason being is because, yeah, when you first initially flick that switch, the current that was like trickling through I3, because you had 4.55 amps going through there, some would have gone down there, some would have gone down there. That's Kirchhoff's current law. It was conservation of charge, really. So we had 2.73 amps going down through I2, we figured that out there. So that means we must have had 1.82 amps going through here. So immediately when you flick the switch, there will be 1.82 amps flowing through here, and then it'll backflow through I2. I can't think of the top of my head. I'll think of a better explanation for that soon, maybe. Right. Next question. Explain why all currents will be zero after a long time after the switch is opened. Simply put, the energy is stored inside the magnetic field of the inductor. As that magnetic field collapses, you get a change in flux through the coils of the inductor. That induces a voltage. That voltage then drives current around the circuit. That current goes to the resistor, and the voltage is used up, or the potential difference is used up via heat of these two resistors. So that's pretty much the crux of it. I'll just pause and write it probably slightly more succinctly than that. Right, so I've said more succinctly, I1 will be zero as it's an open circuit. I2 and I3 will decrease to zero as the magnetic field of the inductor collapses. The energy stored in the, I'll just shorten to B field, the magnetic field is given off as heat by the resistors. Maybe I should put R1 and R2, they don't give you very much space. But whatever. Right, next question, what do we have? Pulse magnet utilizes charge stored in a large capacitor, this one here, to drive a very large current through a coil of wire, this coil here. Pulse magnet can be modeled as an RCL circuit, DC RCL, not AC, with a coil of wires represented inductance L and resistance R. After closing the switch, the magnetic field rises to peak value that can be larger than possible in a conventional DC electromagnet before decaying away. An example of magnetic field versus time for a pulse magnet can be shown here. Explain why the field takes time to build to its maximum value and why it eventually decays away. So for any magnetic field, I don't know if they briefly touch it. It's a Biot-Savart law. Biot-Savart law? It's French. I'm not French, so I don't know how to say it. But B-I-O, I don't know how to spell either. Savart, something like that there. I might say that just, shall I Wikipedia? Nah, I can't be bothered. But I've always known it as Biot-Savart law. So magnetic fields depend on the current. That's it. So if you have a huge amount of current, you get huge magnetic fields, and that's why MRI machines, all the wires inside of MRI machines, because an MRI machine makes some of the biggest magnetic fields that humans can make. Not the biggest, but some of the biggest. And they use liquid nitrogen, and I think they use liquid helium as well. So they get the wires down to a couple degrees Kelvin, so then they become superconducting. And if they're superconducting, you can get huge amounts of currents through these tiny wee wires. Not infinite, there are rules. Anyway, so explain why it takes some time to build to the value and why it eventually decays away. As you get a rapid change of current through the inductor, you get a back EMF. Inductors oppose rapid changes of current, and they do that by, when you have a change in current through the inductor, it creates a magnetic field which then passes through all the other coils, which then induces a voltage, and that voltage opposes the voltage that was used to create it. That's Lenz's law, and that's basically what takes time for that to happen. And then why it eventually decays away? Well, eventually it will decay away because energy will be dissipated by the resistor. That's pretty much it. If you don't have the resistor here, these are what are these called? Oscillating circuits. These will resonate. And if you have a capacitor, an inductor, and you run it at the resonant frequency, so if you have a wire coming down here and these here are, and your frequency is at the resonant frequency of these two using the impedance matching formula, or reactance matching really, because you need to have the same reactance for that frequency, you get infinite reactance. And they will oscillate. The magnetic field collapses, which then creates current, goes back and charges capacitor, and the capacitor then gets full charge, then discharge, and just switches back and forth. Right, I better pause right now so then keep going. Right, so this is kind of I don't think it's an amazing answer. I think I could have sat down, probably spent maybe 20 minutes to really fine craft it. Well, anyway, so the greater the magnetic field, the larger the current needed. As the inductor opposes rapid change in current via the back EMF, as a capacitor discharges, change in current decreases, reducing the back EMF until the capacitor is discharged. It eventually decays, and now this is why it eventually decays away. I've said it eventually decays away as a finite amount of energy is stored in the capacitor. As the current oscillates from capacitor to inductor, energy is dissipated in the form of heat by the resistor. So this resistor here will just dissipate all the energy off. If you had no resistor and you had an imaginary circuit, it would just oscillate forever. And sometimes you get asked questions about what's the resonant frequency of that oscillation and so on and so forth. And if you want to know the resonant frequency, is just F naught equals 1/2 pi square root LC from memory. Right. Suggest the practical reason why the circuit is preferred to using a DC circuit with the same current. Practical reason. Not sure whether they mean battery, but if you had the amount of current required to make a magnetic field that big, so 75 Tesla, is swear word huge. You need to have a huge amount of current. And it's a pulsed magnet. I don't even know what would they be used for. It'll create a lot of heat, crazy amounts of heat. So it'll make a whole lot of heat, and if instead of using a capacitor that you could just bang and fire away, and you had a massive battery bank of like, I don't know, lithium ion batteries, you need to have a switch that would close and open and close and open. You'd like a pulsing switch, and you can buy them. You can buy them, but from memory they're kind of expensive. So I'll just pause and write it, and then yeah. Right, so I've said running large amounts of current for extended periods will generate unmanageable amounts of heat in the wires. Maybe I should have said that would have melted them. In the answer schedules it does. Also, you could use an expensive solid state relay. So here's a little fact for you. In cars and motorcycles and most other things that have lights, when you turn your light on for, like when you're on the dash, you turn the light on to turn like the headlights on, the circuit doesn't run up. All the current doesn't run up through your dash through that little switch. What that switch does is when you turn that on, it allows current to flow through. Normally they're magnetic, through like a wee coil, which then activates a magnet which closes, and that closes the other circuit, which is used to then have current go from the battery through that circuit to your like car lights and then back again. So that's how relays are used. You normally always use relays for like large amounts of current, where you don't want to be, like you could have a massive switch where you'd be like, switch it down. But normally you just have a little flicky switch, you flick. That would close the first circuit, which then drives an electromagnet, normally the electromagnet, which then closes the second circuit, and then the primary circuit runs. That's it.